everyone, welcome back to our seminar. And today, Josse, Dobben, and Bruyn is going to tell us about the gonality of graphs.
Thank you. Thanks for having me. So today I'll be talking about gonality of graphs, which is a relatively new graph parameter, which has its origins in algebraic geometry, but it also has all these interesting connections with, well, first of all, algebraic graph theory, but then also structural graph theory and parametrized algorithms. And I'll give a broad outline of the topic and the field in my talk today. Okay, so I'll start with a brief history of gonality. So in the late 1990s, it was observed by several authors that graphs can be viewed as discrete analogues of Riemann surfaces. And then in 2007, Baker and Bruyn and another paper by Matt Baker established a concrete connection that goes beyond the analogy, that actually allows you to translate from curves to graphs and lets you prove theorems in one or the other by going back and forth and proving it in the other field. And also they established connections with chip firing games and abelian sand piles, which had been studied by different authors in very different contexts. So ever since this work by Baker and Bruyn, there has been an explosion in research just on this intersection between graph theory and algebraic geometry and tropical geometry. One result I would like to mention here is this paper by Coles, Drijsma, Payne, and Robeva, who proved, or they gave a new proof of a classical theorem in algebraic geometry using combinatorics. And then in recent years, also there have been these connections with the structural graph theory and parametrized complexity. Yeah. Okay, so what is gonality? So the gonality of an algebraic curve is a measure of its structural complexity somehow. I'm not going to go into the algebraic geometry today, I'll focus on the graphs. But let me just say that there are two different but equivalent definitions for gonality of curves. And they lead to inequivalent analogous definitions on graphs. So there's one definition in terms of what's called divisors or chip firing games. And another one in terms of indexed harmonic homomorphisms to a tree. This gives two new graph parameters, the divisorial gonality and the stable gonality or tree gonality, which in general are not directly related, at least not by an inequality, but they're very similar in spirit and somehow capture the same ideas. And today I'll be giving an outline of each of these forms of gonality and the results and open problems about them. So I'll start with divisorial gonality. Okay, for today's talk, a graph will be finite, connected, loopless multigraph. So important to note here is that I do allow parallel edges, and I'm assuming that everything is connected. The Laplacian of a graph, as most of you know, is this matrix LG equals D minus A, where D is a diagonal matrix with on the diagonal entries the degrees of the vertices, and A is the adjacency matrix. And since we're working with multigraphs, it has multiplicity, so it's not necessarily a 0-1 matrix. Okay, a divisor on a graph is an integer vector on the vertices of the graph. And this term divisor, that's coined by the algebraic geometers because this is the graph analog of a divisor on a curve. So we'll see this more often in the talk, that sometimes these terms seem a little weird, but that's just because the algebraic geometers called it that. Okay, so two divisors are equivalent if their difference is in the image of the Laplacian, but really in the, so if there's an integer vector x such that the d minus d prime is Laplacian times x. So in other words, they're equivalent if they're in the lattice spanned by the columns of the Laplacian. And in the next slide, I'll show you an example of equivalent divisors to get some feeling for what this means. So chip firing games. Equivalence of divisors can be thought of in terms of a chip firing game. So we imagine now our graph as being endowed with chips on the vertices. So I'm pretty sure this term chip derives from poker chips and not computer chips. So we won't be affected by any chip shortage or whatever. And also we note that the number of chips on a vertex can be negative, in which case we say that the vertex is in debt. Okay. And then firing a vertex that's moving, it's moving one chip from V to each of its neighbors. So for instance, if we choose this gray vertex down here and we fire it, then that means that it gives away one chip to each of its neighbors as depicted here. And we end up with this divisor or chip configuration. And in terms of Laplacian, you can just write this as subtracting the Laplacian times like one of the standard basis vectors. Okay, this is then, I guess, this is the minus LG of 1V for this vertex. And if we pick a different vertex, then you're going to add a different divisor, but it's a fixed divisor for each vertex that you choose. Here's another one. Okay. And then because addition is commutative, the order of firing doesn't actually matter. So we can also fire subsets. So that's equivalent to firing each vertex in S in any order. So for instance, if we choose this subset, then firing the subset, it means firing all the vertices in the set. And then some of these edges, they see chips being fired both ways and they cancel out, so we can remove them. So the net effect will be that you fire only across, only over edges that go across the cut from S to S complement. And again, it's adding this fixed divisor for the set S. Okay, so firing all of V has no effect because, well, all these edges cancel out, nothing happens, no edges going out. So firing S can be undone by firing the complement of S. And now it's very easy to see from the linear algebra that the divisors D and D prime are equivalent if and only if D prime can be reached from D by firing moves. So for instance, this divisor that we have here is equivalent to the one that I started with before, which had the 8 chips on this vertex. Okay, so now we have an interpretation of equivalence in terms of chip firing. Now we move our attention to non-negative divisors. So I write D and D prime greater than equal to 0 if it is non-negative on every vertex. So if we have two divisors that are both non-negative and they're equivalent, then it's always possible to go from D to D prime by firing subsets without ever going into depth in any of the steps in between. So here's a quick proof. So these divisors are equivalent, so we can choose some x such that D minus D prime is LGX. And then since the all ones vector is in the kernel of the Laplacian, we may add multiples of that to it to get to assume that x is non-negative. And then we let t be the maximum entry of x, and we define these level sets S1 through ST, where kind of in the reverse order. So S1 is like the top level, so it's only the vertices in V that have the maximal entry in X. And then S2 is the vertices of v for which xv is 1 fewer than the maximal entry, or it's a maximal entry. So you go by these levels. I guess before I go to the next step, you note that this is an increasing sequence of subsets. So every time you get bigger and bigger. And you can write x as the sum of the indicator vectors of these sets Si. So if you subsequently fire each of these subsets, then that will turn D into D prime. And now to show that we never go into that, here it is again, the sets are all subsets of each other. So suppose that we're looking at some step I. And we want to show that after the ith step, no vertex has gone into that. So if V is not in the set that's fired in the ith step, then also because of these inclusions, it hasn't been in any of these previous sets. So it has only received chips so far, right? It's been on the receiving end of the chips. So the number of chips is at least as much as it started with, which is non-negative. And then similarly, if V is in Si, then it will be in Si plus 1 and so on until the last one. So it will only give chips away until the end. So now the number of chips is at least as much as it's going to end up with in the end. So again, it's non-negative. So this shows that you can always go between equivalent non-negative divisors without going into that. And this will be our mental image to keep in mind. Okay. So now we come to the first results about these chips, divisors. We define the degree of a divisor as the total number of chips, so just the sum of all dv. And we write div plus k of g for all the non-negative divisors of degree k. And now we can define the rank of a divisor. The rank, it's the maximum k, integer k, such that for every non-negative divisor of degree k, there is some divisor d prime that's equivalent to d, such that d prime is greater than equal to this divisor e. So we imagine that we are playing this game where our opponent chooses any e that's a non-negative divisor of degree k, and we have to rearrange using chip firing moves, rearrange D so that it gets at least as many chips as E has on each vertex individually. And the maximum k for which we can do that, that's the rank. I'll also get to an example of this in the next slide. But first, I just want to mention that like one of the big results in this field is that this rank behaves similarly to the rank in algebraic geometry of a divisor. And you have this Riemann-Roch theorem that says, well, if G is a graph and K is this canonical divisor, which has on every vertex degree V minus 2 chips, then you have this relation between the rank of D and the rank of K minus D in terms of the degree of D plus 1 minus G. G here is what the algebraic geometers call the genus, though I guess many graph theorists would object. It's the first Betti number of the graph, or the cyclomatic number. Okay, so this is like the first big result that started the whole thing in 2007. I'm not going to get into the proof of this, but now we get into gonality of graphs. So the divisorial gonality, here just for your recollection, I have the degree and the rank. We define the gonality of a graph as the minimum degree of a positive rank divisor. And that means it is the minimum number of chips in a chip configuration, so that if my opponent appoints any non-negative divisor of degree 1, which means just a divisor that is 0 everywhere and 1 in one place. So if my opponent points to any one vertex in the graph, I should be able to reconfigure the chips to get at least one chip on that vertex. And now we can show this in pictures. So for instance, if we take a cycle and we put chips here and here, suppose our opponent wants us to bring a chip to this vertex, then we can fire a subset like this and not go into that, and fire again, and then we get a chip at the desired position. And you can also do it the other way, and that shows that the divisorial gonality of C9 is at most 2, because this configuration uses 2 chips. Now similarly, if we start with a grid, then we can put chips on one of the rows or one of the columns, and we can move them around through the graph using firing moves like this. So you fire like the initial first k columns, and that will move the chips one column to the right. And that shows that the divisorial gonality of this grid 6,4 is at most 4. And finally, on the Peterson graph, our favorite example, if you take these 4 chips, then I claim that you can reach all vertices with one firing move. So to get to these 2 vertices, we can fire like this. And that'll take one chip across here, one chip across here, and no one goes into that. If we want to reach these 2 vertices, then we can fire like this. And again, each of the 4 vertices that carry a chip have one edge going out, so none of them go into that. And finally, to reach these 2 vertices, we can fire everything except these 2, and no one will go into that. And this shows that the divisorial gonality of the Peterson graph is at most 4. Are there any questions so far?
Could you just spell it out once again why it cannot be bigger than 4? Just to understand the definition.
Okay, so the divisorial gonality is the minimum degree of a divisor D that has positive rank. And so here I have shown a divisor of degree 4 that has positive rank. And so the gonality is at most 4.
Okay.
So in general, giving an upper bound for the gonality, that's just you show a divisor and you show that it has positive rank. And then giving lower bound for the gonality, that's the hard part.
And what was E? Oh, sorry, what the E is number of edges, just right? In the rank definition.
No, so this is another divisor.
Oh,
I guess it's not.
Okay.
Yeah.
Good. Okay. Thank you.
Maybe not the best letter, come to think of it. Anyway. Okay. And so now previously we had the Riemann-Roch theorem from algebraic geometry, which had combinatorial counterpart. And then there's another theorem in algebraic geometry which has a counterpart, and that's which has a suspected counterpart, I should say. So that's a Bruyn conjecture. In algebraic geometry, this is a theorem, but it's not known for graphs, at least not for divisorial gonality. So again, we have this definition of the genus or cyclomatic number. And then in algebraic geometry, there is this complicated formula rho that prescribes that if this number rho, it's defined like this, but I mean, the precise definition doesn't matter. If this number rho is non-negative, then every graph of genus G has a divisor with rank R and degree at most D. So in algebraic geometry, this is known, but for graphs, this is a conjecture. And if we specialize this to the R equals 1 case, then this is saying that every graph of genus G has a divisor with rank 1 of a certain upper bound on the degree. So this is an upper bound on the gonality. And if you work out the formula, you get this G plus 2 over 2 rounded up, or G plus 3 over 2 rounded down. This is a conjectured upper bound for the gonality. But again, we don't know this to be true for all graphs. So some partial results have been proved in recent years. So it's trivially true for dense graphs. So if the number of edges is at least 3 times the number of vertices, then this upper bound that you get here, it's larger than the number of vertices. And that's always a trivial upper bound on the gonality, because just putting one chip on every vertex is certainly a positive rank divisor. And then Atanasov and Ranganathan proved this for all graphs of genus at most 5, which already was quite involved for them to show. And some other special cases are known, like it's known for Cartesian product graphs where each of the 2 factors is non-trivial, so has more than one vertex. And it's true for these metric graphs, which are not actually graphs, but like more closely related to tropical geometry. I'm not getting into the definition of metric graphs today, but it's maybe serves as partial evidence that it might also be true for graphs. Okay. And towards that end, Baker made another conjecture. This gonality conjecture was conjectured by Baker, but there was another subdivision conjecture. So here we study from a graph also its regular subdivision. So we subdivide each edge into the same number of parts. So sigma 1, we subdivide every edge into 1 part, so we leave it as it was. Sigma 2 subdivides every edge into 2 parts, so we add 1 vertex, and so on. And the limiting object of the sequence of subdivisions is the metric graph. Well, sort of. I'm kind of sweeping some details under the rug here, but there is this notion of a metric graph. And the important thing for us is that a divisor retains its rank when we embed it in a regular subdivision or in the metric graph. So if you have a positive rank divisor on G, then it's also a positive rank divisor on sigma k and on gamma. So you get these inequalities that the minimum rank of a positive divisor is at most that on G. And Baker conjectured that actually you have equality throughout for every graph. And then since, in particular on the left here, we have these metric graphs, and there the Bruyn-Noether theorem is known to be true. So if you prove the subdivision conjecture, then you also prove the Bruyn-Noether conjecture. But what we showed is that the Bruyn-Noether conjecture is, or sorry, the subdivision conjecture is actually false. So there exist graphs, even simple bipartite graphs, GK with divisorial gonality 6K, but they're metric graphs, and their subdivisions have divisorial gonality only 5K. I think I'm going to skip the proof here in the interest of time, but just there's this construction of these, whatever. Okay. Maybe briefly pause again to see if there are any questions at this time. If not, then I'm moving on, because I really want to get to the connections with tree width. So tree width of a graph, it's this graph parameter in structural graph theory. It measures somehow the tree-likeness of a graph. It has this, it plays an important role in the graph minor theorem, for instance, and also in theoretical computer science in parametrized complexity. And then back in 2014, Dion, Gijswijd, and I, we proved that actually the tree width is a lower bound on all forms of gonality, basically. So on divisorial gonality and on stable gonality, and there are some other forms which I'm not telling you about. We have equality for some simple enough graphs, so for trees, cycles, grids, and complete multipartite graphs. But in general, they can be far apart. You have graphs GK, which have 3 with 2 and divisorial gonality K, so they can be arbitrarily far apart. And I guess since this is a survey, I should mention that a better bound has since been found. It's this scramble number, SN, that was defined by Harp, Jackson, Jensen, and Speeder. And basically what they did is they took our proof and they noticed that it holds more generally. And the scramble number is just defined as the graph parameter for which the proof still holds, like the largest graph parameter. It has not been studied before this, but it's very useful actually in practice because often it actually gives you better bounds. So that was a great discovery by them. Right. So that about concludes the first part. I guess there's these other research going on in gonality. Maybe I shouldn't have put them all here. Like one thing that people study also is higher gonality. So instead of looking for a minimum degree divisor of rank 1, you can look for a minimum degree divisor of rank R. And if you look at the sequence for all R, this gives you like the gonality sequence of the graph. And people are interested in like what are the properties of these sequences, what kind of sequences can occur as gonality sequences, and a number of other problems, which in the interest of time, I won't talk too much about. I'll just briefly pause here again to ask if there's any questions about the first part of the talk. And after that, I'll move on to the other gonality. Okay. I'm not seeing any questions at this time, so I'm moving on to stable gonality or trigonality or stable trigonality. Different authors use different combinations of the words. Okay. So again, I stick with the same convention that my graphs are finite, connected, loopless multigraphs. And now we look at graph homomorphisms. And this is just a reminder, again, I think most of you know this. A graph homomorphism, phi, it's a function from vertices and edges of G to vertices and edges of H. So that vertices are mapped to vertices, edges are mapped to edges. And if E is an edge between U and V, then phi E is an edge between phi U and phi V. And we point out that all our graphs are loopless, so endpoints of an edge are never sent to the same vertex. There are some other authors out there also consider homomorphisms where you are allowed to map edges to like a loop, but we don't do that. And so in particular, the inverse image of every vertex is an independent set. Okay, so now we get to harmonic morphisms. So I guess I use this notation E of V for the set of edges incident with this vertex V. So edges going between V and V complement. And now, again, this terminology comes from the algebraic geometers. They say a finite morphism is a pair phi, R phi, where phi is a graph homomorphism, and R phi is this weight function, or they call it index function on the edges. So to each edge of G, we assign a non-negative integer. Like here, for example. So on the left, we have G on top, this path T at the bottom. The homomorphism just sends everything vertically down. And we have these weights or indices at the edges of G. And here on the graph on the right, I have no weights, so we assume that these weights are 1 if no weight is mentioned. Okay, and then such a morphism, a finite morphism, is called harmonic if it satisfies the following property. For every vertex v on top, I guess I have an animation here, there is some constant m phi of v, such that, okay, I'll show it in the animation. So if we pick this vertex v on top here, and we go then to phi of v, and we want that for every edge e prime incident to this vertex at the bottom, the sum of the weights of the pre-image of that edge, where you only look at pre-images that are incident to the vertex we started with, that sum should be independent of E prime. So I'm saying that if we go down here to this vertex, then if we take this edge, then the total weight up here is 2. And if we take this edge in the other direction, then the total weight of the edges again is 2. So that's the harmonic criterion. And again, if we take this vertex, go down here, look at this edge, look at its pre-image, and only like the pre-image is adjacent to the vertex we started with, the sum is 3. And on the other side, the sum is also 3. And on the right, again, we have these, all of these have weight 3. So these are 2 examples of harmonic morphisms from G to a path in this case. It's a bit technical, but just we think of it as a graph homomorphism which somehow has this extra structure. Yeah, that makes it even more special. Okay. And then a basic proposition on these harmonic morphisms is that they have a degree. So if you look at these examples before, this is just, all these formulas is just saying, if we go look at some edge here, then the total sum of the pre-images, now we're not just summing the pre-images that are incident with one specific vertex, but the total sum of all pre-images of this edge, that's the same as the total sum of the pre-images of every other edge. And also for the vertices, like these m phi that I defined in the definition, these sum up to the same value in every pre-image. And that's the degree of the harmonic morphism. So this is a degree 3 harmonic morphism. And now we get to the definition of stable gonality. And this uses this notion of a refinement. So a refinement of G is a graph G tilde. It's obtained from G by 0 or more operations of the following type. We may subdivide edges or add a leaf. So leaf being a vertex of degree 1 that we add. And then the stable trigonality or the stable gonality of G is the minimum degree of a harmonic morphism from a modification of G to a tree. Oh, sorry, refinement. So yeah, so it's a minimum degree of a harmonic morphism G tilde to T, where G tilde is a refinement and T is a tree. So for example, if our graph G looks like this, well, this does not have a homomorphism to a tree. And why not? Because a tree is bipartite. So everything that has a homomorphism to a tree also should be bipartite. That's just, by the way, because like a bipartite coloring can be pulled back along the homomorphism to give a bipartite coloring of G. But now we make this refinement of G tilde, where we subdivide this edge in the triangle and also the outer edges in the triangle. And this has the following harmonic homomorphism even to this path below, where all the edge weights for the harmonic homomorphism are just 1. So this is an example showing that this graph on the left here, it has stable gonality at most 2, because there is this refinement G tilde and a harmonic homomorphism of degree 2 from G tilde to a tree. And now I made this remark about G not being bipartite. So for the stable gonality to even exist as a finite number, we need these refinements somehow. And actually a non-trivial result is that the Bruyn-Noether theorem now, so what was a conjecture for divisorial gonality, for stable gonality is a theorem. So we have this upper bound on the stable gonality of every graph. It's this genus plus 2 over 2 rounded up. And that in itself is non-trivial, because from this definition, certainly it's not obvious that this number should be finite at all. Like these harmonic homomorphisms, it's very strict requirement, and certainly you need to subdivide things to make it bipartite. And in fact, the only proofs that we know for Bruyn-Noether theorem for stable gonality is Baker's original proof, which ran through algebraic geometry. It's using the Bruyn-Noether theorem from algebraic geometry. And then recently, Drysma and Vargas, they proved it using tropical geometry. So it's a bit more hands-on, but it's still a very complicated geometric proof that it has a combinatorial flavor, it has a geometric part, it's really tricky to get it right. So it would be really interesting to find like a simpler combinatorial proof here for graphs, but so far that's an open problem. Right, just want to briefly pause again, see if the definition of the stable gonality is somewhat clear. Any questions? Guess not, then I'm moving on. So as the last part of my talk, I would just like to revisit tree width and show you a proof sketch that tree width is a lower bound for this stable gonality. I'll just briefly recall the definition of tree width. So tree width is defined in terms of these tree decompositions. A tree decomposition of a graph G is a tuple T, this collection XT, where T is a tree, and these XT are subsets of the vertex set of G, and we have one such subset for each vertex in the tree. And these subsets are called the bags of the decomposition, and they should satisfy the following properties. So first, for every vertex of G, if you look at the collection of all tree vertices such that the XT bag contains V, then that forms a connected subtree, so in particular non-empty. So every vertex occurs in at least one bag, and the bags that it occurs in, it's like a connected subtree. There's no gaps, yeah. And then the second requirement is that for every edge, there is some bag that contains both endpoints of the edge. Okay, so if D is this tree decomposition, then the width of D is the maximum size of a bag minus 1. And this minus 1 is just a normalization that's common in tree decompositions to make it so that the tree width of a tree is 1. And in fact, the tree has tree width 1 if and only, sorry, a graph has tree width 1 if and only if it's a tree. And then the tree width is the minimum width of a tree decomposition of G. Right, so now we get from, how do we get from harmonic morphisms to tree decompositions? Well, we recall that I promised earlier that you have this inequality, tree width less than or equal to stable gonality. And both are these minimization problems. So what I want to do is just find a way to transform a harmonic morphism to a tree decomposition, and that shows directly then the inequality. And in fact, we can do that, as I showed here in joint work with Hans Botlander, Dion Gijswijk, and Harry Schmidt. We showed that there's this algorithm to convert a harmonic morphism from a refinement of G to a tree, if it has degree at most k, and it transforms it into a tree decomposition of width at most k. And the proof is really pretty simple, because you already see some tree structure here in the stable gonality. And in fact, we can use the harmonic morphism directly to write down a tree decomposition. So here's a proof sketch. Right, so we need to start constructing this tree decomposition. If we have a vertex, so T here is the tree in the harmonic morphism, and the tree decomposition that we will build will be a refinement of T, so a subdivision of the edges of T. So we start with the vertices in T, and then we associate the pre-image of T, that will be the bag for that vertex. So for instance, if this is like a small part of the harmonic morphism, these vertices get mapped to this T, then we get this bag for T that contains V1, V2, and V3. Okay, next, if we have an edge in the tree, then we need to find intermediate bags between XS and XT that are not too large. And we do that by passing from XS to XT one edge at a time. Okay, what do I mean by that? So here I've shown an edge in the tree T and its pre-image in G. So here its pre-image consists of these 4 vertices U1 through U4, and they have these edges going between. And now we need to go from this bag XS on the left to this bag XT on the right. We think of all these edges going across here as being directed in one or the other direction. So initially we think of them as all being directed towards U1. And then this bag is just like the set of vertices in total that have an arrow coming in. And now we will flip these directions one by one, and that will create new bags. So first we start with this edge up here. We flip the direction. So first we make it bidirectional, I guess. This creates a new vertex with an incoming arrow. So we create a new bag which has that vertex V1 added to it. Then we remove the old direction here. And now U1 no longer has an arrow coming in, so we create a new bag again, which has U1 removed. And we move on to the next edge. So this edge, we flip it. Okay, V1 was already in there, so there's no new bag. We remove the old one. Now we go to this edge, we add V2. Okay, there's a new bag. And we continue in this way until eventually all edges have flipped. And this will give actually a tree decomposition. So first of all, because of the way we constructed it, it's clear that for every edge, at some point, both endpoints are in the same bag. Also, if you look at any one vertex UI, then it occurs certainly in the bag for phi of UI. And then around that, like some of the subdivided edges for each of its adjacent edges. What am I trying to say? So it's going to be like a star around this vertex, right? So this U1 occurs up until some point, and then it disappears and it never comes back again. So it's connected. So this is a tree decomposition. And it's also not too large. And that's because at any step throughout this transition from XS to XT, the size of the bag is at most the number of edges plus 1, right? we have one edge that's directed 2 ways and the other edges are directed 1 way. And the number of edges in this cut is, I guess it's at most a degree. If you count the multiplicities from this weight, then it's exactly the degree. So we get this upper bound that the bags have size at most degree +1. And then because of the -1 in the definition of tree width, you get that actually you end up with 3 decomposition of width at most k. So that proves it. Okay. Great. And now some people are actually using this in parametrized complexity. So in parametrized complexity, you study these computational decision problems which have an input of size n and a separate parameter k. And now you want to give a more fine-grained analysis of the complexity as a function in n and k. So you have all these complexity classes, like xp is the class of all parameterized problems that can be solved in time. Polynomial, where the degree of the polynomial depends on k. And fixed parameter tractable, FPT, is all parameterized problems that can be solved in time like a fixed polynomial times a constant that depends on k. I had all these examples, but in the interest of time, I won't go over them. So we get to problems parameterized by stable gonality. I just want to mention that many problems are fixed parameter tractable, which means easy in some sense when parameterized by tree width. Like for instance, coloring graphs of bounded tree width, there are polynomial times algorithms to do that. And then they also become fixed parameter tractable when parameterized by stable gonality, because the stable gonality is larger, right? So if you look at graphs of bounded stable gonalities, certainly they will have bounded tree width. So problems that are easy when parameterized by tree width are also easy when parameterized by stable gonality. But in fact, stable gonality can deal with problems that tree width cannot. So really, there's really interesting applications here in parameterized complexity. So there's this class, again, don't worry too much about the definition. There's this class of harder problems somehow. And then Botlander and his co-authors, they showed that there are these several problems that have been studied by other authors before. Minimum, maximum out degree, undirected flow with lower bounds, and capacitated dominating set. And these problems are hard, like XNLP complete or XNLP hard when parameterized by path width or tree width, but they come fixed parameter tractable when they're parameterized by stable gonality. And you can sort of think of this as being like a P versus NP complete dichotomy. It's a bit different, but certainly these classes are believed to be distinct. I think this is a stronger problem actually than P equals NP. So if you prove that FPT is not equal to XNLP, then that implies P not equals NP. So, but the key takeaway is that somehow this stable gonality is a very appropriate parameter, even in parameterized complexity, because it can deal with problems that tree width cannot. Right, so just to recap, graph gonality, it's this vibrant research area. It has all these deep and interesting results and all these connections between these totally unrelated fields, like algebraic and tropical geometry. It has these chip firing games, graph homomorphisms, structural graph theory, and parameterized complexity. And I really think that it has the potential to be or become an important graph parameter in structural graph theory or in parameterized complexity. But there's more work to be done to make it so. And that concludes my talk. Thank you for your attention.
Thank you so much, Josse. Okay, are there any questions? Oh, my only question is, does it relate to quantum homomorphisms in any way?
Not that I'm aware of.
No, okay.
Yeah, I guess you could try to define like a quantum version of these harmonic homomorphisms, but
yeah, well, we just started studying gonality. We can define quantum gonality as well.
yeah.
Okay.
Perfect.
Okay. Okay. Well, that was my only question. But that was a very interesting talk. And are there any questions?
So, do you believe that this Bruyn-Netter conjecture for the divisorial gonality is true, or do you think it might be false?
Yeah, so for a long time I thought it should be true. Just going back to the slides, but then when we came up with this counter example for the subdivision conjecture, I think this is really strong evidence to me that also the Bruyn-Netter conjecture might actually be false.
Mm-hmm.
But we've tried to extend this to also become a counterexample to that conjecture, but that we couldn't do. That still seems to be like the harder conjecture.
Mm-hmm. Okay, thanks.